Hey folks, I wanted to first start class with an apology. I'm sorry for not getting yesterday's lecture recording up until today. Um, I think that probably most negatively impacted the folks who wait around for the lectures, and that was not intentional. It just sort of they got away from me, so I apologize for that. I do not plan to let that happen today. With that. I wanted to also talk a little bit about your exam that is upcoming on Monday. So I'm going to share my screen and I'm going to I always like to write on a PowerPoint slide just because I found that I don't know if anyone's ever used Zoom as a host. There's a whiteboard function and it is the strangest thing, but I have not had a lot of success with that recently. They did an update to it a couple months ago, and now whenever I use the whiteboard, then I find that people are also writing on it alongside me, and um, it's not what I'm looking for. So with here's my PowerPoint backboard or background, so I'm gonna go ahead and get started. Your exam on Monday. First of all, I've had a handful of people who have emailed me and they've requested to take their exam, at very least the first one online. I have no problem with that. Um, whether it's hey, I want to save myself the trip, or, I live in Austin, I live in Killeen, whatever, just email me and say, hey, can I do this? And I'm glad to comply with that. In the event that you want to do your exams in person or you're planning on doing your exams in person, that's kind of the default. If I don't hear from you, there will be a printed copy of the exam for you to take. Um, the only way that you're going to take it online is if I hear from you. I'd really like to get the list of folks who are taking their exams online squared away today. So the sooner you contact me, the better. Um, and I think that everyone who I have heard from has received an email from me at very latest today. If you haven't heard from me saying, "Hey, sounds good. I'm going to add you to the list," then please follow up and email me again. So, there we go. Everyone is going to take an exam that is 40 questions. And for those 40 questions, you're going to have 80 minutes. Um, and I set a time frame of 80 minutes because if you are actually, wait, no, no, no. We have 100. Yeah. So 80 minutes is just my kind of simple way of saying, okay, well, we're going to have time before the exam starts and time after the exam concludes for people to turn in their exams if they're in person. 40 questions, 80 minutes. Now, I think, yes, this is the paper that I've got there that I need. Um, all of these questions are going to be multiple choice. And those multiple choice questions, um, they have anywhere from A through D as correct answers or possible correct answers. Some of them are A through E. Um, at this point in the process of writing the exam, which I have 10 of my questions I feel good about. I'm going to write probably, hopefully, about 10 more today. Um, I am not anticipating any questions with multiple correct answers. Now, what I mean by that is I am not anticipating having any questions that are multiple select questions. So select all of the true statements below. We might have that later on, but not for this first exam. Um, so A through D and sometimes A through E. To answer those questions, I'm going to have questions that have pictures. What is this bond? Which of these is the hydrogen bond donor? Which is the hydrogen bond acceptor? These are all good things to kind of brush up on. I like to ask lots of questions that are application based. because those application questions to me are critical thinking sorts of questions. Now, with that said, it's not exclusively critical thinking questions. There are some questions that are just straight up the single letter code for lysine is, and then K is the correct answer. Spoiler alert there. Um, if I were to ask a question about single letter codes and I wanted to be a more of a critical thinking question, the question would be, and just a second, I get my chat window down. The question would be something like, here are four different letter options or single letter codes: D, A, R, and N. These are your four different answer options. Which of these is a single letter code for a polar uncharged amino acid? And so it's a critical thinking question because then you're going to have to think, okay, well, of these four options, are there any that I can dismiss as non-polar? So they're out of the works together. Yeah, A, alanine, that's out. Polar uncharged. Okay, well, these last three are polar. Aspartic acid is polar negative. Arginine is polar positive, and asparagine is my polar uncharged. So that would be my correct answer for that. Can I get a Y in the chat or a number in the chat if you say, okay, cool, I follow that, or a letter if, wait a minute, I don't follow how I would do that. Awesome. Awesome. So, um, yeah, 40 questions, 80 minutes, multiple choice. In the event I say 80 minutes right now, and now I'm having these second thoughts of like on the first day of class, did I say 2 hours? If I said 2 hours, I apologize. 80 minutes. That's what the duration of the exam is going to be. Um, so that's what you should kind of account for. Now, with that said, do I think each question is going to take 2 minutes each? Nope, I don't. There's going to be some that are going to be 10 seconds. Um, and then there are going to be some that might take you the whole 2 minutes. And you might have to work through, like, okay, here's my thought process. Here's why this is wrong. Here's why this is wrong. Um, everyone can use a 3x5 index card. And I just say index card because that's what is whenever I hear 3x5, I think index card just because it's what I used as an undergrad for flashcards and studies. It does not have to be an index card, so don't go to HEB and buy a bunch. Instead, just get a piece of paper and cut it. Um, and for that index card, you can use front and back. Um, there are definitely going to be some questions that you can get directly from an index card. And what I mean by that is if you say, okay, well, I struggle with the single letter codes, um, I'm going to, use your space on that index card judiciously. And what I mean by that is if you remember alanine is A, glycine is G, don't put that on that index card. That's not worth your time. Instead, just say like, okay, glutamine's a funky one. I'm going to put Q for glutamine, and I'm going to put the three-letter code of GLN for glutamine, so that I'm using this space kind of with high value. Everyone can use that 3x5 index card. Now, I want you to go ahead and plan out as the semester goes on. You will be able to use a single index card for each exam. When the final exam is, you will be using a 3x5 index card. So we're going to keep with the same size piece of paper. The rationale there being that as you get more comfortable with the material, you're going to need to you're going to be able to retain more of it, so you won't need to write as much of it down. So go ahead and plan that out. And, soon it will be every week when you're taking an exam, think back and say, okay, well, I put this information on there. I didn't use that. So I'm getting rid of that. Um, Okay, then let's see. Is there anything else that I really need to bring up about the exam? 40 questions, multiple choice, breakdown of the material. Um, so basically, our material breaks down into a couple of different groupings, and I'm going to go with the PowerPoints. Intro, water, amino acids, protein structure, prostruct, um, pro function, and last but not least is enzymes. And whenever I write an exam, I kind of come up with rough numbers for each different category. Um, So here's what you should expect. And these are all subject to change a little bit, not dramatically. But about 5 questions from the intro, about not eight, 4 water questions, about 8 amino acid questions, roughly 10 protein structure related questions. Protein function is going to be about 7. And last but not least, enzymes are going to get about 6 of them. So that's a rough number of kind of the breakdown of everything. Like I said, these are subject to change a little bit, but if you come into class on Monday and you see an exam that has 40 questions over water, then something catastrophically strange has happened. Not catastrophically wrong, just strange. How could I put together, why would I skip over amino acids to have 40 questions about water? So that's what I think you should anticipate for this exam. I try to distribute like the difficulty kind of evenly. I don't really want to have questions that are like extremely difficult. Some topics are a little bit more inherently challenging than others, but that's what we got. I've got your learning objectives that I think you should look at. I've got, I think, 10 questions on the practice exam published. So work through those. And I think those are good representative questions of both the application, specifically when it comes to like thermodynamics. There's questions about thermodynamics, entropy, free energy change, and enthalpy that I think are good application questions that if you can answer those, you're probably going to be in pretty good position to answer the questions on the actual exam. Now, I'm going to be transitioning over to the PowerPoint, um, or our PowerPoint for class. Um, Dr. Wheeler is going to be proctoring your exam this Monday. Um, if you are taking the exam online, then you can join our Zoom meeting and I will be sitting in there fielding any questions. Dr. Wheeler will have that Zoom open, so if you have any questions, you're welcome to come up to the ask her and then she can communicate it to me, or you can, jump on that Zoom there. Um, but other than that, I never write an exam thinking like, ooh, I hope everyone has lots of questions for me. Because I hope that I write an exam that's clear enough for you to like make sense of it and aren't like, this doesn't make any sense. You don't have a correct answer here. So I'm working very deliberately to make sure that you guys have a good exam this upcoming Monday. But if anyone has any questions, you're welcome to ask now or hang around after class if you have some specific for you. But now I'm going to go to our PowerPoint because we got to finish 2 slides on myoglobin and hemoglobin. Maybe it was just 1 slide. Okay. Um, hmm, okay. Yeah. So almost our last slide. This slide right here was kind of the important like meat of the matter slide. Um, this is an instance where bisphosphoglycerate, so if you're at high altitude, bisphosphoglycerate is basically going to enable your hemoglobin to deposit more or release more oxygen to your tissues than it otherwise would. So, you know, essentially what this slide should mean to you is, oh, um, yes, I believe it is in Chem 100. I'm like 99% sure on that. I'm going to make a note to myself. Um, where I'm planning to take a screenshot from Cat's Web, grab that, throw that up on the Canvas site. Um, okay, so at high altitude, bisphosphoglycerate is a good thing. It helps you release more O2 to the tissues. So although bisphosphoglycerate does favor the T or tense inactive form of hemoglobin, the deoxy form of hemoglobin, at high altitude, that's a good thing. Um, because when you can't get as much oxygen as you would like, um, bisphosphoglycerate comes to the rescue and helps you out a little bit. Now, movements of the oxygen binding curve, it's pretty much binary. It's moving left or it's moving right. An oxygen binding curve is not going to shift up, it's not going to shift down. A shift to the right is going to indicate that you are going towards the T state. And if you are shifting to the left, you're moving closer to the origin. The shift to the left is indicated by this green dotted line right here. And that shows that our affinity for oxygen has gone up. Our affinity for oxygen going up is a result of our P50, or sorry, our P50 in response to that will go down. So oxygen binding curves shift to the left, shift to the right. Our T state of our protein and our R state of our protein, those are allosteric proteins or allosteric states that our protein can be in. Allostery is essentially two different states that a protein can be in. There are allosteric regulators that we talked about, or allosteric effectors. We talked about three different allosteric effectors. One of them was a proton, because hemoglobin is a pH sensitive protein. A pH sensitive protein. If this protein is in an acidic environment, you're going to be favoring the T state. The reason for that is because, well, His 146 is an amino acid that at a lower pH, its chances of being protonated are more likely, which means, and I'm going to say protonated, and I'll go ahead and say when protonated, then a ionic bond forms, and that ionic bond that forms stabilizes the T state of our protein. So from the standpoint of someone who likes to breathe, I don't particularly like that, but I understand kind of its essential function. Now, another allosteric regulator that we talked about was carbon dioxide. Carbon dioxide is an effector for a couple of different reasons, or CO2 is a big deal because one, CO2 plus H2O yields HCO3 minus and a singular proton. Now, what this means is that when CO2 is in your bloodstream, hydrogen ion concentration goes up, pH goes down. Therefore, you're kind of in effect stabilizing that T state because of this carbonic anhydrase reaction. Now, another thing that carbon dioxide can do is, and it's kind of it's a fun word. I'll give you a hint. It starts with a C and it ends with an arbamation. That's right, carbamation. So a carbamation is when CO2 gets covalently bound to the N termini of the protein. So it gets bound to the N termini of hemoglobin. So what that means is that hemoglobin is a CO2 transporter. It moves CO2, but it moves it differently than the way that it moves O2. Our last allosteric regulator is bisphosphoglycerate. Bisphosphoglycerate just inserts itself in the middle of that hemoglobin protein, locking up the T state, preventing or delaying or negatively impacting the transition from the T state to the R state. So any of those things that we kind of remove, then we will shift to the left. So if we are able to dilute away bisphosphoglycerate, then we're going to move to the left. If we're able to replace CO2 with O2, then we're going to move to the left. If we are adjusting the pH from, let's say, 6.8 all the way up to 7.2, we're going to see our curve shift to the left. And then last but not least, another allosteric regulator that we talked about was O2. O2 is an allosteric regulator because of the fact that, well, it's our homotropic effector, and it's a positive allosteric regulator because when hemoglobin binds O2, positive cooperativity is observed. Now hemoglobin wants to bind more O2. Okay, now one of our last two slides. Fetal hemoglobin. A fetus receives O2 from its mother's blood via exchange through the placenta. Fetal blood has a higher affinity for O2 than the mother's. Why is that? Well, fetal hemoglobin is a little bit different. Fetal hemoglobin, sometimes represented as HbF, has a different composition. Rather than having a pair of alpha subunits and a pair of beta subunits, it has a pair of alpha subunits and a pair of gamma subunits. So the sequence of those proteins, gamma and beta, are going to be a little bit different. Now, what that means is the intrinsic oxygen affinity for HbF is very similar to HbA, adult hemoglobin. So this is kind of weird right here. Fetal blood has a higher affinity for O2 than the mother's. Fetal blood, not fetal hemoglobin, fetal blood. The intrinsic oxygen affinity for fetal hemoglobin is similar to adult hemoglobin, HbF versus HbA. The reason for that is HbF has a much lower affinity for bisphosphoglycerate than adult hemoglobin. So what that means essentially is in the presence of, let's say that you had HbA and HbF, and they're both Pac-Mans. And then we had BPG as the little Pac-Man ball. HbA is going to chomp that up so much more easily than HbF due to the fact that they have structural differences. So hemoglobin adult or adult hemoglobin will get that BPG so much faster and more easily than fetal hemoglobin. Basically, it's sucked up so that fetal hemoglobin can't get to it. And if fetal hemoglobin does not bind to bisphosphoglycerate, well, it can more easily transition from the T state to the R state. So the way that I always kind of think about this is, let's say I'm going to say, here's a red blood cell. Or actually, let's just say this is in vitro. Test tube. If we add BPG, HbA, and HbF, and let's say that we had all those three components added in, you might, or it's very likely that you would see HbA bound to BPG. And there might be some free BPG. There might still be some free HbF. So despite the fact that there's bisphosphoglycerate in that solution, that fetal hemoglobin says, no, the concentration's not high enough for me to actually bind it. So I'm just going to ignore that. What you would not see here is HbA. that HbA is going to go after that bisphosphoglycerate and say, oh, okay, cool. Well, the concentration of bisphosphoglycerate is low enough that I'm going to bind to it. Fetal hemoglobin, whatever. And that's really just fine because fetal hemoglobin is then going to be like, great, I wanted to bind oxygen. That's what I'm here for. So, what accounts for this? What accounts for this is that adult hemoglobin has a histidine at position 143 in the beta chain, whereas fetal hemoglobin has a serine at this position. So keep in mind, this beta chain, that's one of the subunits of adult hemoglobin, because adult hemoglobin is alpha 2, beta 2, two alphas, two betas. Fetal hemoglobin is alpha 2, gamma 2. So two alphas, two gammas. Now, this is kind of what we talked about yesterday, where we were looking at the ionic bond that stabilizes the T state. And I said, oh, what happens if we mutated that histidine to an alanine? Are we still going to have that ionic interaction? No, we're not. Here, what we have is a histidine residue that chances are is involved in some sort of ionic interaction. So, what that means is that histidine can form a positively charged cation. Serine, can anyone give me the classification? Add it to the chat. How would you classify serine as an amino acid? Boom, boom, boom. I've got the closed captioning on my screen, so I like to read that out. And it doesn't completely capture my enthusiasm, but it did process boom with the exclamation mark. So I think my hands up were what it picked up on. Serine is a polar uncharged residue. Histidine is a polar positively charged residue. The interactions that these two amino acids are going to participate in are fundamentally different. One can participate in dipole-dipole interactions. One can participate in hydrogen bonds pretty easily. The other one can do, well, chances are those two as well as an ionic interaction. An ionic interaction is going to be stronger than a dipole-dipole interaction. So that's at the heart of this. This is an example of, well, one residue change produces a different affinity for something, whether that's bisphosphoglycerate or oxygen. Now, the change of the positively charged histidine for a neutral or polar uncharged serine reduces the binding affinity of BPG to that fetal hemoglobin. Now, with that said, this is an example of a variation in kind of a naturally occurring protein. There are other abnormal hemoglobins. Now, what I want you to take away from this slide right here and this table right here is not necessarily, oh, I've got to remember these, but instead, whenever you hear about a mutant or a mutation within a protein or a sequence variation within a protein, it's important and I think valuable to think about the implications. So here what we have are hemoglobin variants. And if you look at all those names, there's lots of cities, there's lots of locations on there. And chances are, I don't know the case for all of these, but chances are this is where they were identified. So I was born in Milwaukee. I have not sequenced my hemoglobin, but there's a chance that I have this mutation. I'm not exactly sure, but it produces or promotes methylmyoglobin formation. Now, like I said, I was born in Milwaukee. That doesn't guarantee that I have this, and that's in part because my mom is from the western side of Wisconsin. My dad's from the Milwaukee, so maybe neither was a carrier of this. But my point here is that we've got all these variations. We've got all these different mutations. And I don't know about you, but I don't see any that say like death because the effect isn't necessarily death. A sequence variant is not going to necessarily mean, oh, well, this is how somebody dies. Instead, it's like, well, here's a structural difference. So, BIBA, for instance, leucine H19, or sorry, a leucine. So, this is one thing that I want you to be familiar with respect to notation is typically what you will see is the wild type hemoglobin residue. So we'll use this. Then in this case, when it comes to hemoglobin, they identify the helix. Because remember the helices of hemoglobin are like A through H. Helix number or helix letter H, residue number 19. And then we've got number 136. That is the specific numbered amino acid in this polypeptide in the primary sequence. That is mutated, and then our alpha, meaning our alpha subunit, and then that is mutated to a proline. Quite often, if you see mutations in other proteins, you might just see something like this, L136P. So this means that the wild type protein has a leucine at amino acid number 136. There is not a leucine, but instead there is a proline. But when it comes to hemoglobin, there's a lot more known about that protein. It's very well studied. So there's a lot more information provided. I don't expect you to remember these or anything like that, but if I were to ask you something like, hey, decode this, I would like you to be able to do that. So then you could say like, well, helix E7. Or helix E7 is amino acid number 58. But again, this is not going to be the highest priority. So what these do is they alter the quaternary structure or the tertiary structure of hemoglobin, and that destabilizes hemoglobin to the extent that red blood cells lyse, causing potentially hemolytic anemia. And in some of these, they may favor the oxidation of Fe2 plus to Fe3 plus, which could cause cyanosis due to the increased concentration of methymioglobin. This last item, that is relevant for these three right here. Boston, Milwaukee, and Iwate. I'm not exactly sure how that's pronounced, but that's my best guess. Okay, so the mutations that can result in hemoglobin are quite a bit, they have a little bit of variety and diversity. Okay, now we are going on to our discussion of enzymes. If you look at our calendar for this class, enzymes are something that we will revisit several times. And the reason for that is because we're going to introduce different layers and levels of like enzyme function throughout this course. Right now for this, what I want you to get is just kind of like a basic introduction. So enzymes starts with an E, ends with an S. Enzymatic reactions. This isn't too much of a stretch, but what I'm going to do and what I will try to do most often is have a contrast between enzymes as a biological catalyst compared to like an inorganic catalyst. If I use biological catalyst as a phrase and then I also use organic catalyst, chances are when I talk about an organic catalyst, I'm not talking about an enzyme, despite it being from a organic organism. When I say organic catalyst, I'm thinking about catalysts that you learn about in organic chemistry. So I will do my best to say a biological catalyst versus an inorganic catalyst. Now, what I want you to recognize about this is we have a series of different reactions. Here's the enzymes. These are the specific names for the enzymes. One of the things that you will quite often see when you're talking about enzymes is you will see the term end with ASE. That suffix is usually a good indication that you're talking about an enzyme. For example, does anyone know the first enzyme in the pathway known as glycolysis? If you do, add it to the chat. That's right. Hexokinase, ASE. That ASE is that's pretty synonymous with an enzyme. A kinase is a specific type of enzyme, which we will visit later on. So ASE is a good suffix to be like, okay, we're talking about an enzyme. Now, all of these enzymes, I don't want you to stress about what they do because I'm not going to introduce that at this point. But what I want you to look at is these enzymes will catalyze specific reactions. Those reactions can be catalyzed in the absence of an enzyme. And when they are, they will basically have a rate like this. So 28 times 10 to the negative 16th. Okay, what does that mean? Well, to put it simply, or actually, let's go with this one right here. Carbonic anhydrase. I switched to that one because we've talked about carbonic anhydrase. What that does is H2O plus CO2 produces HCO3 minus and a proton. A uncatalyzed rate of 1.3 times 10 to the negative first is the same as 0.13, and that is these units K negative or to the negative first power. Think about this as if you were to mix up one molecule of water and one molecule of CO2, well, that would be done, let's see, 0.13 times per second. So that reaction gets done 0.13 times per second. So let me translate that. Um, it would basically take about 10 seconds to complete this reaction because roughly 13% of the reaction gets done per second. Could everyone give me a number in the chat if they follow that, and then a letter if, wait, I think that math is wrong, or I'm not sure about that? Okay. So I'm going to say 10 seconds to do RXN one time. Okay. Now, if we compare that to our catalyzed reaction, so this is our enzyme catalyzed reaction. That is done 1 times 10 to the sixth. 1 point, let's see. So that's 1, 2, 3, 4, 5, 6. Okay, so essentially with the enzyme catalyzed reaction, this reaction gets done, well, that's K cat per second, which is essentially that number per second. So that reaction is going to get done 1,000,000 times per second. Now, give me a number if you think that enzymes are something that are good and basically help you kind of live. And give me a letter if you think, no, I'd rather let the non-catalyzed reaction go. Okay, good. We got a lot of enzyme popularity. And, part of that is my bias, but 1,000,000 times per second compared to it takes about 10 seconds for the reaction to get done one time. So I'm doing my best sales pitch on enzymes. Buy in early. It's a good decision. Now, enzyme catalyzed reactions, this is a thing that, well, actually, before we proceed, could anyone tell me in the chat what are proteins made up of? Amino acids. Fantastic. Proteins have a primary structure, which is covalent bonds that stabilize it. Secondary structure, which might have an alpha helix or a beta sheet. Those are backbone hydrogen bond stabilized. Tertiary structure, and we're just going to go with a monomeric, a single polypeptide, but a tertiary structure where you've got R groups that interact with one another. And those R groups could, have ionic bonds or hydrogen bonds that stabilize them. Well, an enzyme, and for this class, what we're going to focus on is enzymes are biological catalysts. So, what that means is they are molecules that are biological in origin. So, a living thing produces them. And though not completely, most of the time when we talk about enzymes, they are proteins. So, this is kind of like A square is a rectangle, but a rectangle is not a square. So an enzyme, most of the time, are proteins, but a protein is not necessarily an enzyme. That's an important thing to remember. Now, with that in the forefront of your brain, what is an enzyme typically made up of? Typically, enzymes are made up of amino acids. So I say typically because the ribozyme is an RNA molecule that has enzymatic activity. So that's the only reason I'm not saying absolutely every time. But more times than not, enzymes, and for this class, what we're going to focus on is enzymes being made up of amino acids. So try to keep that straight. And this is one of the difficult parts of this class where you're building on this information and you start at a 10,000 foot view and then you go down to like a 1 inch view and then you have to zoom back in and out and everything. Okay, so enzyme catalyzed reactions. Here is an example of, well, let's see, in brown, we got some alpha helices there. That's great. And then if we look right, so here's an alpha helix, and then here, right here, and here, and here, beta strands, which make up a beta sheet. So enzymes have a primary structure many times. And actually, you know what? Just I'm going to avoid qualifying. I'm just going to kind of speak and paint with a broad brush. Enzymes have a primary structure, a secondary, a tertiary, and sometimes a quaternary structure, just like a protein. The biggest difference is that they can catalyze a reaction. So many times when you look at something like this image right here, which is a protein structure with basically the reactants that it is acting on. Now, we've got our enzyme, then we've got our substrates. Our substrate is the term that we use to refer to an enzyme's binding partner. This is different from a ligand. The only thing that makes it different, however, is that a substrate is going to be broken. A substrate is either going to be broken or it's going to be modified in some form or fashion. This is different from a ligand because ligands, there's no bond making or breaking whenever it comes to a ligand binding. Now, after that, when we talk about something known as the active site, we're talking about a protein's active site. We're talking about the spatial location in the 3D protein. So, where in the 3D or tertiary or sometimes quaternary structure of the protein, where are the amino acids that are involved in making and breaking these bonds? Now, just as a little bit of an aside and a little bit of a preview, I said making and breaking bonds. So, if we're talking about making a bond or breaking a bond on a substrate, do you think that an amino acid like valine and valine's R group, think for a minute, what does valine's R group look like? Now, what comes to my mind whenever I think about valine's R group? Yep, methyls. I think about a non-polar molecule. I always think of valine and I think of V. Now, do you think that an alkyl group like that is going to be really good at making and breaking bonds? And before you answer, do you think that those atoms, do they have lots of electrons that they're ready to push around and pull and everything like that? A valine, a methyl group. No. So when you think about an active site, what I want you to do is anytime you hear the term active site, I want you to think like, okay, what are the amino acids that make up that active site? And I want you to kind of come back to, okay, well, it's got to be able to make and break bonds. It's got to be able to push electrons, push and pull electrons. So something like an aspartic acid, glutamic acid, you can form ionic bonds. Then asparagine and glutamine. And actually, you know what? Your polar residues. Just paint with a broad brush. Your polar residues are more than likely going to be the ones in the active site that are involved in manipulating the substrate. Okay, now this is another representation of a protein or of an enzyme. And this is what's known as a space fill model. This model right here is known as a ribbon diagram. So in a space fill model, basically this is a more of an approximation of, hey, here's what the protein looks like, or here's what the enzyme looks like, and all of the space that the electrons from the atoms on this molecule can be are here. So it kind of looks like a cloud as well. But that's essentially what it's doing. It's illustrating here's the electron clouds in the space that they occupy. Now, this is the specific enzyme known as lysozyme, which we will revisit later on. Lysozyme is an enzyme that breaks up LPS or lipopolysaccharide in bacteria. Now, it's going to bind its substrate right there. It has a substrate binding site. And what it's going to do is it's basically going to grab onto the enzyme and then grab onto the substrate and then reposition it so that the active site amino acids can establish any sort of those bonds. Can you spell those model terms? Oh, sure. Um, Spacefill, and I'm just going to do this previous slide was the ribbon diagram. Okay, so when it comes to an enzyme shape, these are the big points. Identifying the substrate binding site, and identifying the active site. Now, when it comes to an enzyme catalyzed reaction has a couple of different players. Um, these different players, here what we have is our enzyme depicted here. And then above that, or outside of that, we have two substrates. There are some enzymes that have two substrates. There are some enzymes that have one substrate, some that have three. We will refer to these as substrates A and B. Now, one of the things that's really important about reactions and how they take place is to identify, well, when is one, or what's our sequence? Well, what we've got here is a complex that results. Now, in terms of the sequence, we're going to get into the details of that as to does A bind first and then B bind second, or does binding of A, is that essential for binding of B? That's a little bit of a detail that we're going to get into in a little while. But that was our ES complex. So this notation, E and S and ES, this is what's known as the Cleland notation. Cleland. It's kind of like the Cleveland notation, but somebody forgot to spell all of Cleveland. The Cleland notation. And that's what ES stands for. Okay. Now, in our next model, our enzyme changes the result in the reaction between substrates A and B. What the enzyme's effectively doing is bringing these two substances in very close proximity so that the reaction can actually take place. We note this as the ES complex. Now, if you remember in Gen Chem 2, one of the things that you talked about was, I remember these graphs that looked like this. And I think that the x-axis had temperature on it and percent maybe as reaction. And you saw these curves that looked like this. And it was, you raise the temperature and the reaction's more likely to happen. But then if you raise the temperature too high, your likelihood of the reaction happening actually kind of decreases. This was all about, or one of the key things was, yeah, if you increase the temperature, the reaction's more likely to happen. But it's not quite that simple because you need the reactants to be kind of positioned properly. You need the front of one to hit the back of the other. If they hit front to front, those two reactants are not going to react. Well, what an enzyme is going to do is it essentially puts the two substrates in the perfect position so that they are primed to react with one another. Now, substrates, what they are going to do after that reaction has taken place, and what I want you to recognize here is we've got substrate A with a kind of magenta ball bound to it, and substrate B does not have that magenta ball bound to it. That ES star is basically where the reaction is beginning to take place. Now, here, what we have is what's known as the EP complex. In this case, both of our products are still bound to our enzyme. It's a subtle difference, but that kind of magenta colored ball, it's not magenta, but this ball right here has moved from substrate A to substrate B. And in the process, has substrate A changed? Yes, it has. It lost that magenta-ish ball. Has substrate B changed? Yep, it gained that ball. So A makes a change to become C. B makes a change to become D. Now, those are our two products. What this is illustrating is the Cleland notation, where we've got EP, the EP complex, the enzyme product complex. The enzyme is still bound to the products. It has not yet released them. And then after that, what we get is our products released and our free enzyme that stays behind. So E plus P. So product C is released and product D is released. These two substrates and products are going to be released at different times. And the exact timing of it varies from reaction to reaction. Now, what I'm showing here is a very, I don't know if I would say deliberate, but I've kind of drawn out to illustrate a bi-substrate reaction, where a reaction where you got two substrates. Now, the way that we look at it all is best depicted here. E plus S yields ES. The enzyme is bound to the free substrate. Then we've got our reaction taking place where ES star is, EP, where our products are still bound to our enzyme, and then E plus P, where our product is actually released. So this is a good notation or a good overall show of what is taking place in an enzyme catalyzed reaction. Now, all of these steps are reversible, but one of the things that's worth noting about these steps being reversible is there is still the thermodynamics that you have to account for. Some of these reactions are less likely to take place considering the free energy change that's required to go from the products to the reactants. Now, does anyone, if go ahead and add to the chat a number if, okay, I'm cool, I follow this so far. Okay. Okay, great. Now, whenever we talk about enzymes, there's a number of things that we need to discuss. One of them is, and this is kind of an advantage of an enzyme, is they are very, very specific. So they're only going to bind to one substrate and they're only going to produce one product. So they have binding specificity. They also have flexibility. They also have an electronic environment that helps them catalyze their reactions. Now, just as we saw with heme or hemoglobin as having a prosthetic group, enzymes will also have coenzymes. These are compounds that are effectively, they're kind of like a prosthetic group in that they give them a function that they otherwise would not have. So, heme, for instance, helps oxygen bind to hemoglobin. In the absence of hemoglobin's affinity for oxygen is very low. Coenzymes kind of do the same thing in the sense that they enable an enzyme to bind to a specific substrate or establish a bond or bind to a substrate with a greater affinity. Now, when it comes to substrate binding, there's a couple of different mechanisms. One mechanism is known as the Fischer mechanism. And this is where you have a substrate that its shape very much so complements the shape of the active site of the enzyme. So here what we have is our E and S, and then this is our resulting ES complex. Another mechanism similar to this is known as the induced fit model or the Koshland mechanism, in which case you have a substrate of a known shape that doesn't exactly complement or is not exactly complemented by the active site of the enzyme. And whenever this substrate binds to a portion of the enzyme, well, then the enzyme basically closes in and wraps around that substrate, still forming the ES complex. Now, what an enzyme is going to do is
Can I
in one
ask you a
way.
quick question?
Oh, go ahead.
Can we go back really quickly? So I just want to make sure I understand this right. It's the enzyme or the substrate that's changing to fit which one?
On the right-hand side, that's the enzyme that is changing.
Okay. Okay, thank you.
Sure, absolutely. So, yeah. Um, Now, when it comes to what an enzyme is going to do, is keep in mind that an enzyme is like a protein in that it's got some flexibility, it's got movement to it, so that it can basically engulf a substrate, close it off, and then whenever it does, it can kind of impose its will and break bonds and make bonds accordingly. Now, I think what I'm going to do is have this be our last slide for this first exam. Um, so we won't get all the way into enzymes. We'll just kind of stop with enzyme action and free energy because we talked about free energy previously. So this is a free energy diagram showing an uncatalyzed reaction, and we're going to compare and contrast that to the free energy diagram of an enzyme catalyzed reaction. Now, our substrates or our reactants, I want you to feel comfortable using those two terms interchangeably, substrate and reactants. Um, they will have a certain level of free energy. The enzyme, or sorry, in a uncatalyzed reaction, the reactant's free energy is at this point right here, an arbitrarily high number, we'll say. Now, in order for the reaction to take place between those two reactants, well, what they need to do is they need to reach a transition state free energy. So they have an activation energy. If there is not adequate activation energy for these two reactants or three reactants, however many, to reach this transition state free energy, the reaction will not take place. So they will have to rise up to this point right here. And whenever they do that, then the reaction can take place and the products will, in theory, well, have a lower free energy than the reactants themselves. Now, a couple of things that are worth noting. We have our activation energy, which is from our substrate's free energy to our transition state free energy level. So I'm going to put a number. Let's call this 50, 100, then 0. Okay. So the activation energy for this was 50. Let's just go with joules. The free energy change, or the overall free energy change for this reaction was from our initial point to our product point. So that is negative 50 joules. Whenever we have a enzyme catalyzed reaction, what we're going to notice is that the activation energy is lower. So our reactants alone do not have to reach this point because, or they do not have to reach that transition energy state because in theory, what's happening is our enzyme is providing or it's inducing that substrate to change. So this is our activation energy, which is where our substrates need to get to. Our overall free energy change between our substrate or our reactants and our products does not change at all. So when it comes to an enzyme catalyzed reaction, ECAT versus UNCAT, we'll go with activation energy. And then free energy. In an enzyme catalyzed reaction, our activation energy is lower. Our overall free energy change, no change. In an uncatalyzed reaction, when we compare that to an enzyme catalyzed reaction, this is higher. But the overall free energy change does not change. Sometimes people refer to this as a delta G T state. So a change in the change of free energy of the transition state. An enzyme has to, I always kind of think about these free energy diagrams as almost like roller coasters in the sense that, well, the roller coaster that the enzyme is going to take you on is maybe not nearly as exciting as the uncatalyzed reaction because it doesn't go as high, but that's fine. So we have to reach this free energy or the transition state free energy level in order for the reaction to take place, whether it's in the uncatalyzed reaction or in the enzyme catalyzed reaction. This is a free energy diagram that I want you to be able to pick out different parts from it and answer questions about changes in overall free energy and changes in transition state free energy. Now, that's slide number 15 for our next block of stuff. We're going to start with enzymes, and that will start at slide number 16. Now, I'm going to go ahead and stop my recording, and we've got time, so